Okay, so we should be recording now. Yes, we are recording. Great. Good. All right, so let's go take a look at your question. So X is normally distributed random variable. How often will X be within 2.18 standard deviations of the mean? That is, what is the probability that X will be between negative 2.18 and 2.18 standard deviations of the mean? Hint, draw a standard normal distribution with the given information. Okay, so let's go paste that question in here.
Yeah, I thought, I know these are from quizzes that I've done,
That's okay.
but at the same time, I also get the feeling that getting them right will help my understanding. So,
Yeah, it will. It will. Okay. I'm trying to paste it in and it's not being cooperative, so we'll just do it by flipping back and forth. Okay, so the numbers are negative 2.18 to 2.18. All right, so the hint that they gave us was that we should draw a standard normal curve,
yes.
and that's a really good hint. You want to do that. Hang on just a second here, grab the right wire. I got so many.
I tried doing that.
Okay. Well, and then what you want to do is once you've drawn that, you want to put all the information that they gave you on the drawing, or as best as you can, okay? So let's go ahead and let's put in, there's a glorious x-axis, and here is our standard normal bell-shaped curve over the top of it. So this is the z distribution, so we know mu is equal to 0, and sigma is equal to 1. In the model notation, that's n of 0 by 1 is what the standard normal is. Now, the two numbers that they told us that we should plot on here, they said, take a look. We want to know how much of the x, or what's the probability of the x residing between those two numbers. So to do that, we're going to come over and say, well, look, one standard deviation is roughly about there and about there. Two standard deviations then would be roughly here and here. So we want to know what's the probability of being between those 2 points. So if that's negative 2.18 there, and this is 2.18 here, the probability that they're looking for is going to be the shaded region in here. So this stuff right in here. Yeah?
Yes.
Okay. So if I find the area of that blue shaded region that I'm painting in right now, I'm going to find the probability of the value residing between those 2 points. So notationally, what they want is the probability. Let's go back to black here again. We want the probability of negative 2.18 being less than z being less than 2.18. So far, so good?
Okay.
Okay, you good with that? We're all hunky-dory, because now we got to go calculate that. All right.
Yeah, I think the calculation is where I
Okay. All right. So the thing you got to realize is that our book, like many textbooks and many software packages, some probability from the left. That's real common. So if I find out that area right there, I know it's going to be the same as this area right here.
Yes.
And those red areas are going to be the same by symmetry, right?
Yes.
So if I can find out what that area right there is, then I'll know that if I double that and subtract that from 1, that's going to be the area of the blue stuff.
Yes.
So in other words, writing that mathematically, I know that this is going to be equal to 1 minus 2 times the probability of z being less than negative 2.18. Remember that the red stuff here, let's do that in red, maybe it'll help. These two here, we know those are the same, aren't they, right? Okay, so that's this right here. The red stuff is that, all right?
Yes.
Okay, so if I take the red stuff away from 1, what's left over is the blue stuff, which is what I'm looking for, right?
Yes.
Okay, so in terms of doing that in R, using it to calculate this, what we would do is we'd go 1 minus 2 star, you got to be explicit about your multiplication, p norm, that's an R, really, p norm of negative 2.18 comma 0, comma 1. So let's go get R up front and center here. Go get our console, because we're just going to do this stuff in the console. We don't need, well, obviously, if it's a quiz, you're doing it in the console. If it was a homework assignment, you'd be doing it in a script, in a R markdown file. So it's 1 minus 2 times P norm of negative 2.18, comma 0, comma 1. And it comes out to about 97%. So intuitively, I'm liking that answer. Why? Well, let's go back and take a look at the picture again. Does the blue stuff look like it's about 97% of the picture?
It looks like most of the data.
Yeah, it does, doesn't it? And you know, 100% is all you can get. You can't get any more than 100%. So yeah, it looks like it's most of the data, doesn't it? So I'm feeling pretty darn confident about my answer.
It kind of brings to mind the 68, 95.
Yep. You're on it. Exactly. Because if you think about it, you're basically what? You're a little more than 2 standard deviations above and below the mean, right? So what'd you get back for your area? Oh, a little more than 95%, didn't you?
Yes.
Right? Because 2 standard deviations, 95% of the area should be within 2 standard deviations of the mean in a normal distribution.
Right.
Is that better?
That's better. I think I was getting lost between calculating, lost with the z-score, like the difference between the actual data.
Okay, well I think I got an idea where you're going there. So let me take a stab at that. All right, let me just give you a little heads up on that. Okay, so if we were to draw a normal distribution, it doesn't have to be standard. It could be any of them. But let's just, for the sake of making ease, we'll do standard normal. Okay. All right. So if this is standard normal, that means it's modeled by n of 0 by 1, and that's our z-axis, and we know this is centered at 0. Okay. Well, in that last example, they gave us z-scores. They gave us numbers. In other words, a position on the axis. So say this is negative 1.83, okay? And my question would be, say, perhaps, what is the probability of z being less than negative 1.83? Well, what that's going to be is it's going to be this red shaded region down here, isn't it?
Yeah.
This red shaded region is that probability. In other words, that is this red stuff right here. So to do that, to actually calculate that, I would go P norm, and then I would go negative 1.83. I cleverly chose one with a left-hand tail, so I don't have to do any of that 1 minus stuff or the false. That works also. 0 by 1, okay? And that's going to give me back that red shaded area. All right, but what if the question was asked differently? What if instead of giving me a position on the axis and asking me for a probability, let's say this time, again, we're working in Z, they said, you know what, I got a cutoff right here, and what I've got is I've got this area, and I happen to know the area this time. So I know that this blue shaded region right here just happens to be 0.37. In other words, that's the area. It's 37% of my distribution. And then the question would be, what the heck is that point right here? In other words, what's the z equal to? So if I give you an area this time, and now what I want is I want to know what the position on the axis is. Are you understanding the difference in the question? Is that kind of...
I feel like part of me is understanding, but part of me is still kind of fuzzy. Okay,
so back up here on this one, notice that they gave you a position. They gave you a value on the axis, didn't they, right? That's a position on the axis. That's a point right here. Down here, what did they give you? They gave you a probability.
Yes.
So what they wanted in the first problem is they wanted to know the probability. So you were given position,
Yes.
and then what you want to know is what is the probability that goes with that. So in
Yes.
this case, you're given the probability, and what they're going to want to know, what is the position?
The position, yeah.
Is that making more sense?
It is making sense, yeah.
That's position, really. Okay, so how would I go about doing the calculation down here in the second one? How would I actually get it to do that for me? Well, I'm going to need Q norm this time. And what Q norm does is he says, again, everything in the binomial distribution and the normal distribution, and later we're going to work with some other distributions, it'll be the same thing. It's always summing from the left-hand side. So it's coming over from the left and moving from the left to the right, okay? So the area you put in the command has got to be the area from the left, all right? So Q norm, so our Z value this time is going to be equal to Q norm. And then I put in 0.37, comma 0, comma 1. So let's go back over. Go ahead, Kathy, before I do it.
So for the sake of understanding it, maybe we could go over again what you do to calculate by hand the position or the probability.
Okay, how do you do that by hand? Well, let me finish this first, and then I will show you.
Okay.
We'll either go running away screaming or say, okay, that's cool, let's go back to R, all right? One of the two, okay? Let me go finish this first, okay? So let's go back over to R, and we're going to go, okay, Q norm, because the math gets really intense. 0.37, comma 0, comma 1. And that number right there is the position on the axis. So if I come back over to here, that point, negative 0.33, that's not a probability this time. That's a position. That's this number right here. This number on the axis right here is negative 0.33. Okay, remembering that this right here, the center was at 0, right?
Yes.
Okay. All right. So I'm going to give you a 30-second tour of how you would try and do this by hand if you were trying to do these calculations by hand. All right. So if you had a normal distribution, this curve right here, this bell-shaped curve, is given by a mathematical function. F of x is equal to e to the minus x squared divided by the square root of 2 pi.
Oh, great.
So if you put that into your calculator, it'll give you this bell-shaped curve. You with me? Okay. Now, if I want to find area under that curve, this is a continuous function, and so I have to use a tool that finds continuous sums. That's called the integral. It's a calculus function, all right?
Okay.
So, for example, if I wanted to find the area up to negative 0.33, all right? And I wanted to find the corresponding area, this area right here.
Okay.
Okay. Or again, this is Z, and this is normal 0 by 1. Okay. What I would have to do is I would have to evaluate the indefinite integral from negative infinity to negative 0.33 of e to the minus x squared over the square root of 2 pi dx. And when I evaluate that integral, that's going to give me back this area, which, we just happen to know because we put it in there, is 0.37, because I built this to make that would come out to be equal to that, okay? That is a Calc 2 minimum requirement to be able to understand how to do that. So
Okay.
the math's not accessible. We're not going there, okay? So that's how you find the areas by hand. And they didn't even do it by hand back in the day. What they did, because this is a very difficult problem, so what they did is they built tables. And so that's what's left over. So the by hand stuff is you go back and look in the back of the book and look at these ridiculous tables. We don't use tables anymore. That's left over from like, the 19th century. No need for that. Okay, so I'm not saving that. That's going away. All right, but that said, okay, what we can do is we can calculate z-scores.
Yes.
Okay, and so a z-score, hey, somebody else just signed in. Hang on. If you just logged in and you're looking for Math 120 questions.
I think that was me.
No, there was somebody there. That might be your phone, but there was somebody who came in for a moment. Well, we'll see if they come back in. So you can still calculate z-scores based upon your x and your mu and your sigma. And this is very important. Of all the formulas that you're going to see this semester, this is the one you need to memorize and you need to understand it.
Yeah, I do remember that.
Okay. Because we're going to use that one over and over because it's a measurement of position of our observed value x with respect to the purported mean and the purported standard deviation. And that's actually going to be one of the tools that we use when we're doing hypothesis testing. So, but we're going to get more details on that coming after spring break. All right, let's go look at that second question you asked, okay?
Yeah.
Because you had two, so let's go take a look at the second one. So the other one here is the Pew Research one.
Yes.
Okay, so Pew Research in 2012 says typical response rate is 9%. If in a survey of 17,000 households are contacted, what is the probability that at least 1,500 will agree to respond? Use RStudio's p-binom command to find the probability. Enter the command you used along with the output here. Okay, so big hint that we're supposed to be using p-binom because it's telling us that this thing's binomial. So if it's going to be a binomial model, we need to know n and we need to know p. The binomial model has two numbers to make it work, just like the normal one does. So let's go back and take a look. So they're saying that the p is 9%. So the probability of response is 9%. The n, the number of households that they surveyed, was 17,000. So the binomial distribution we're going to be working with is b of 17,000 by 0.09. Okay, so that's the probability of success. All right, so let's think about this for a minute. We can't draw a continuous distribution because it's not, but we can certainly draw an x-axis that represents the number of successes. So x here is the number of successes out of 17,000. You could have got 17,000 people in your group and not a single one of them responded to you. So that would represent 0.
Yes.
And you could have had one person responded to you. And then it could have been 2, right? And then 3, and then ... And then it could have been 1,499, and then it could have been what? 1,500, right? ... all the way up to all 17,000 of them responded to you.
Yes.
So those are all the possible things that could happen. Well, what do they want from us? What are they asking? Well, they're asking, what is the probability of that at least 1,500 would agree to respond? So at least 1,500 means what? Well, it means 1,500 or more, right?
Yes.
So what's the probability of x being greater than or equal to 1,500 is what they're asking you for.
Right, okay.
So what's the chances of getting 1,500, getting 1,501, getting 1,502, all the way up to all 17,000 of them respond, okay?
Yes.
All right, cool beans. So what we're going to do is just to stay consistent is we're going to shade those guys by putting green dots over the top of them. I did that in the lab too, right? I drew these pictures and I said, look, we're going to shade them, right? Okay, so they say use p-binom. P-binom sums up. It's just like p-norm. It's the summer. It sums up cumulative probability structure. The problem for us, as with all of these silly things, is that it sums from the left. All of them do that.
Yes.
Even the TI calculator binomial one, the p-binom and the TI calculator, they call it the CDF, binom CDF, it sums up from the left-hand side. They all pretty much do it that way. So we're going to have to be a little bit tricky here, because what we're going to need to realize is that this red stuff right here, that's the probability of x being less than or equal to 1499, right? And if we add that to the green stuff, which is the probability of x being greater than or equal to 1500, the magenta stuff, or cyan, that's what that is. That's got to add up to 1, doesn't it? I mean, the total probabilities have to always add up to 1. If you take everything you got, all the possible probabilities, and add them all together, they have to sum to 1. That's a fundamental of probability theory, is that the cumulative probability has to come out to 1. So what we want is we want this stuff. In other words, we want the probability of x being greater than or equal to 1500. So we're going to solve this colored equation up here for that. So this is going to be 1 minus the probability of x being less than or equal to 1499.
Yes.
Okay? So now we're supposed to say, how do you do that in R? Well, to do that in R, that's going to be 1 minus p binom. And then I got to put in my x, the p binom command, in case you forget, all right? But you can always do a question mark on it to remind yourself. Oh, I didn't want that parenthesis in there, excuse me. P binom is x by n by p. You put in those 3 numbers in that order, okay? So our x is going to be 15, slow down, Mike, 1499. Although it's not going to make a huge difference, we still want to do that. So it's going to be 1499 by 17000 by 0.09.
Okay.
Okay. This is probably one of the hardest problems you're going to work all semester, just to let you know, all right? Okay, so let's go into R and let's do that. So that's 1 minus p binom. By the way, when I graded it, if they put 1500 in there, I still took it. I didn't ding any points for that. And that's the probability. It's about 79% of the time you're going to get 1500 or more.
Okay.
And again, that's not something you want to try even attempt to do by hand. That's not even the realm of reality, okay? In fact, back in the day, the binomial tables only went up to n equal to 15. And after that, they just said, you know what, you can estimate it with the normal distribution. And so they would do it that way. But there's some flaws with that. You know, it's got to be at least 17,000. It's got to be a really large number in order for the normal probability estimate to be pretty good. But, you know, it works. Okay, so you said you had some more for me. We got through the 2 you posted. But before we go on, though, stop me. Does this make any sense?
I think it does. When you said 0.09,
that's because why? You told me that the probability, the response.
Oh yeah, because it was only 9%.
Yes.
Okay.
So, I mean, the hint when they told you to use p binom in the problem, right?
Yes.
That was a big hint that this is binomial. And so when you're binomial, you know you got to have n and you got to have p. You got to know those 2 things. I got to know the number of trials and I got to know the probability of success.
Yeah, I think I'd forgotten what the problem had said. So it was good to review. I want to check my battery.
Okay.
See where I'm at. I have 36% left.
Oh, you're rocking it. You can go for hours.
Well, maybe 1. Let's see. I think my biggest problem is that I seem to be kind of fuzzy on stuff.
That's, Catherine, that is the way at this point. It's this stuff is somewhat intense. We're almost kind of asking you to sip from a fire hydrant, and it's coming at you pretty fast and furious. But the solace you have is that we're not doing it just once. We're going to keep doing it over and over again. We're going to come back. This was setting the stage for stuff that we're going to be using the same stuff for later on. We're going to be looking at the normal probability distribution and hypothesis testing and the confidence intervals. And we'll be looking at the binomial probability and hypothesis testing and confidence intervals. Although we're going to switch over to using that normal approximation that I was just talking about, just because it makes our life so much easier. So pretty much everything is going to come back to the normal. And then we're going to have one little twist in the game where we have a small sample size. And when the sample size is small and you don't know the standard deviation, which you typically don't, then you have to kind of make up for that. And the way they make up for that is they use this thing called the student t distribution. But it's not really learning all that much new, because it's very, very similar to the normal. It's just it's used to compensate for when you have small sample sizes.
I did see something about the t distribution on Khan Academy.
Yeah,
it says
it's coming.
It said something about how the tails are bigger. Does that
heavier tails?
Right?
What they say is it has heavy tails.
Something like that.
Yeah. So if you were to put them on top of each other, if you were to draw the standard normal and the t distribution on top of each other, t distribution changes its shape based upon what the sample size is. So if the black curve right here, if that's the standard normal, right?
Yes.
Say, okay, say I've only got a sample size, say, of 5, right? And I drew the corresponding t distribution, it would look something like that. It would be squatter. It'd be like somebody sat on a standard normal. It's kind of squished it, okay? And what that means is, look, there's more mass, there's more probability possible out here on the tails. So that's what they say, the tails are heavier, or it's got fatter tails, because there's more probability further down the line than there was with the standard normal. Because remember, the standard normal, once you get past 3 standard deviations, there's not much left in with respect to probability mass. It's pretty much gone. Because remember, between plus and minus 3 standard deviations, you've got 99.7% of all possible probabilities. Well, you round that off and it's 1. So you pretty much got it all by the time you get out to 3 standard deviations.
Yeah.
So that's not necessarily true in the t distribution.
Right.
It changed, like I said, though, it does change its shape. So let's say I made n equal to 15. Well, if n was equal to 15, it's going to start getting closer to the standard normal. It'll look more like that.
Right.
And actually, by the time you let n get to 30, you can't even hardly tell the difference between them. The t distribution just starts plotting pretty much right over the top of the standard normal at that point.
Oh, so that's why they say that, what was it, for the central theorem?
That's part of it, yes. For n greater than 30.
Yeah.
Yeah, the t distribution does that too. For n greater than 30, you're pretty much guaranteed that your sampling distribution is going to be approximately normal. They're actually 2 different things, but they coincide really nicely.
Oh. Okay.
The n greater than 30 is kind of the gold standard. As long as your sample size is greater than 30, you can slacken up the condition of normality and you'll still be okay, because the sampling distribution is probably going to be approximately normal, except for in the most extreme cases where you have just crazy skewed data.
So then, what's the difference between the t distribution and the normal?
The formula that calculates it, for one thing.
Okay.
And the formula, when I mean the formula by that, like a minute ago I told you, for the standard normal, f of x was equal to e to the minus x squared over the square root of 2 pi, right? So that's the function that gives you the black line. The function that gives you these lines is actually in an integral equation. It's not even a nice closed form equation. And it's dependent upon these numbers. You put that number into the equation, that sets it, and it gives you a particular shaped curve.
Okay.
And I don't have that one memorized. I'd have to go look that one up.
Oh, okay.
Yeah, I don't remember the function, the PDF for the t distribution. Better erase this tape. They'll take my my math degree away. My God, you don't remember that? That's a travesty. Okay, so you got some more for me? Got any homework questions or anything we can do?
Homework questions? Not currently.
Okay, how you doing with the confidence interval and hypothesis stuff from chapter 4? Have you taken a look at any of those yet? They're kind of chewy, so you need to get after them. They're not easy questions. There are not that many of them, but
I thought that if I started working on the homework, then maybe I'd understand the discussion better.
Possibly, yeah, that might be. It's nickel half dozen either way. Many times the discussion helps you understand the homework better. But I've got feedback in both directions where some people say, I'd much rather. I used to force everybody. You will go linearly through the module. You will do A, you will do B, you will do C, and you will do it all like this. And I kept getting feedback saying, if I'd only been able to see the discussion question first, I could have done way better on the homework. Or if I had done the homework first, I would have been way better on the discussion question. So I just opened it up, and you can go in any order you want. You just got to get it all done.
Yeah.
So you want to go take a peek at some of the problems and just see if any of them look like you know where to attack them from? Have you even looked at any of them yet?
I've looked at the first homework assignment listed.
Okay.
I was just going through some of the problems before coming online.
Okay.
I don't really want to open RStudio right now because
yeah, that's fine. No worries. I can do that. So let's see. There we go. Why does it still say Spring 17 on it?
Sir Ronald, what was that? I didn't see that on my end.
I think it's because I'm an assignment ahead of you. Well, no.
Okay.
Let me see. Hang on just a second here. Wait a minute. Let me see where I'm at here. Spring break. Yeah, no, this is the right module. Okay, here we go. Assignment. Here we go. Assignment 6. Yes, I was a module ahead. Sorry about that.
I was wondering, how come you didn't assign one of these homework assignments last week?
There's only one homework assignment in the whole set.
For this week?
Yeah.
I thought I saw 2 homework assignments.
There's 2 discussion questions.
Oh.
2 discussion questions, 1 assignment.
Oh. I guess
and there is an extra credit quiz in there also that I put up. I mean, I gave you plenty to do. Trust me. There's lots to do in there.
Yeah. I was getting worried.
No, so there's the reading, and then the reading is really thick. I mean, this is probably one of the harder things that we've had to read, comprehension-wise, as to what's actually going on. And then assignment 6. If we take a look at the template, let's go ahead and get that open. So this is the lab. So these problems, I did quite a few of them on the lab, and then we start the textbook exercises down here.
Yeah. I remember I did look at the first discussion question as well, and then I got kind of freaked out. So I kind of thought, well, maybe I'll look at the homework first and see if that'll help.
Well, last week's office hour, I did the first discussion question.
Oh, you did?
Yeah. Yeah, so if you look at the archive for last week, you'll see pretty much everything you need for the last week's discussion question.
I mean, for the first, I mean, for one of the discussion questions for this week.
Yeah.
Oh.
Yeah, because there's 2 discussion questions, one for last week and one for this week.
Oh wait, so then last week's is still open?
Well, yeah, it was technically due March 6th, but you know, it's still open.
So then it sounds like maybe
This was the one. This was last week's. Didn't you get together with me, Catherine? I forget. Somebody got together with me and wanted to know about.
Oh man, I was so freaked out. I thought I had an extra discussion to do that I hadn't done yet.
You've got 2 total. You got this one, which was, you know, what are the hypotheses from the BBC, right?
Yeah, and I did that one.
Okay, cool. All right. So then the second one, which is coming up, needs to have it done this week. That's
and that's the one that's due to the 10th.
Yes. And this is discussion question 2 on hypothesis testing. It's just basically, this one's kind of more mechanics of hypothesis testing. It's a question on that.
Yes. Oh, that makes me feel so much better.
Okay.
But yeah, I did look at this one and kind of freaked out about it.
Okay. Well, there's really nothing calculatory about it. It's pretty much all, you know, you're going to give back in English. And like, how does she set up the hypotheses? I mean, obviously you can do those symbolically, but you can give those in words too. You know, explain to her in plain English how she should collect the data and carry out the hypothesis test. So that's a paragraph you got to write there. Okay. Suppose she samples 40 adult males and follows an average of 70.2 inches, and then she gets a p-value of 0.0082. What should she conclude? So that's testing whether or not you understand how to make a decision based upon the p-value from a hypothesis test.
Okay.
Interpret the p-value as a conditional probability in context of this question. So what does it mean? What is that actually telling you?
Yeah.
And then suppose that the true average really was in fact 69.1 inches. What type of error could have she made?
Okay.
We talked about the error type in the last discussion question too. So this is getting just more in depth into the nuts and bolts of a hypothesis test before we actually go start doing them. Then the next chapter, we're gonna actually start doing, gonna give you the data and you're gonna do it. You're gonna actually, and you gotta be able to interpret it.
Okay. Oh, this makes me feel so much better.
Okay, so if you've done the reading, even if you haven't done the reading, you have the book out in front of you while you're trying to answer these, it's gonna make a lot more sense.
Yeah.
So I'm focusing mostly these 2 weeks on hypothesis testing, although not in the homework. There's still stuff on confidence intervals. But we will come back and spend some time in the next couple of weeks focusing a little more on confidence intervals too. So don't neglect that just because I'm not assessing that as much as I am the hypothesis testing, okay?
Yeah, no, I'll do that.
Okay, cool. All right, so you got anything else for me? Otherwise, I got a mountain of grading I'm going to get after.
I think I'm good for now.
Okay, cool. I think we'll call this good. I'm going to go ahead and stop the recording.
Thanks very much.